So we've seen three ways of looking at entropy, and I hope everyone now has a pretty solid uh, uh, understanding of entropy. It's actually rather very simple. It's not as ambiguous or arbitrary or vague or magical as what, you know, uh, mainstream media or the general population believes. It's actually very precise and very simple to understand. And in fact, it's one of these things that's so simple, but yet it's so profound because it applies to everything. Any process in the real world can be formulated in terms of entropy and thermodynamics. Okay, so let's do an example now. So we're going to do examples today that require the mechanical approach. And we'll just because that's something that's probably what you've already seen in the text. Okay, so let's do some examples of delta S calculation. Okay, and mostly it'll be the use of ds is equal to 1 over t dq reversible. And so the first one that we're going to look at today is the entropy change delta S for mixing of ideal gases. Okay. And I want you to keep this expression in mind right here as we go through, because this is an indication of the probabilistic nature of entropy. So the other thing I want to sort of, and let me put in S as KB natural log of W, or you might see this as S is equal to KB natural log of omega, where omega is this number of ways or number of arrangements that a system can be found in or realized in. And we see here that S is not something that it represents an average, and that's a very bad word here. It represents many, many states. So remember the first lecture of this course, I kind of said, well, you know, people often use the example of, oh, my bedroom is in a state of entropy, right? And, you know, and this is a misconception because you see here now that one snapshot of your bedroom or room is not representative of entropy. You would have to say that, oh, well, if I were to take snapshots of my bedroom over months and years, right, and you then average or actually you figure out all of those micro states of your bedroom, that would give you a representation of entropy. Looking at your bedroom one day and saying it's messy gives you no information about entropy of that bedroom, as an example. Okay, so I think now you understand that. Now I think you should be able to understand that misconception in terms of looking at one particular microstate or one particular state, one particular arrangement in time. It tells you nothing about the entropy. Okay, and this is why this notion of entropy as chaos or and/or disorder is again inaccurate, because those definitions implicitly carry the assumption that you're looking at one particular state. So you're comparing one state where perhaps something is perceived to be ordered, and then another state where it's perceived to be having disorder. Okay, that's not entropy. Entropy is this collection of all of the states taken together, and that number, the number of ways you can have something arranged at the level of whatever you're interested in, whatever resolution. And so in the case of a bedroom, perhaps your clothes in the hanger, on hangers, and you know, your books on the shelves and what have you, right? And so it's a collection of states, and it's that number that represents entropy in aggregate. There's no one particular microstate or arrangement that is indicative of entropy. That's incorrect. The other way to think about entropy over these microstates, which So here you would have to, in that representation, you know that W is a number, right? So that's where S is related to a number of ways, not just a single thing, but the number. And of course, in this probabilistic expression, you see that there's a sum over all the possible states that are available to a system. And so again, this thing called entropy is not just determined by one configuration, but many. Okay. And in fact, some configurations will contribute more than others based on their probability, right? And that's given by this expression here. We haven't really talked about the form of the probability, as alluded to a Boltzmann factor, the e to the minus beta times this energy is the fundamental probability factor. But at the moment, all we have to appreciate here is that this is a sum over states. It is not a single thing. Okay. Again, I wanted to make sure that that is clear to everyone. Okay. And now, if you go to a party or something and you talk about that, people will probably walk away from you. But in this course, we have to accept what is the reality of it and the way we understand it. Okay, so let's look at the entropy change of mixing, delta S of mixing for ideal gases. Okay, and this will be at constant temperature and pressure. So temperature and pressure are constant. Okay, so there's no dT and no dP. And so we can, let's start with this expression here. So we have n moles of gas A, okay, and this is a gas, and it's in a volume, and I'll show you this in a moment, at T. Plus we have n moles of gas B. Both, again, these are both ideal gases. Okay, and this is a gas. Initially, it will be occupying a volume B, T, and then what we're going to have is something that goes to Na plus B, where we'll have something all mixed together, and we will just have, I'll write this as this combination of A plus B together, okay, is gas, and then volume V at temperature T, okay, and this volume right here, V will be VA plus VB, and now we'll use this pictorially to see what that means. So initially we have a container, okay, and on this side we'll have Na moles of gas A, which is ideal, and the volume on this side will be VA, and there will be a particular T, and on this side we'll have Nb moles of gas B, and there will be a volume V on this side of the container, and this will be at temperature T, okay? And then this is a partition. Okay, and what we'll do in this process is remove the partition. And here what we will have is Na plus Nb. So we have N total moles, which is just Na plus Nb. And we'll have a total volume V, which is now obviously going to be the sum of the two volumes we started with. And we still have T as our constant temperature. Okay. And so this is a rigid box, okay, and obviously there's no insulation because the temperature is constant. So somehow, whether there's any, we have to allow for some way to keep the temperature constant. And you know that if temperature is a constant, then you hook up something to a thermostat. And when you hook up a system to a thermostat, it's no longer isolated, okay, because now you have interaction between something outside of the system, the thermostat, and the system. Okay, and we know that this is just from our intuition that this is irreversible. If I remove this partition, right? And so again, just as with the Joule-free expansion, the experiment starts the moment I remove the partition, where I had these two gases on either side. Again, these theoretical formulations are fine, right? We can do this, and we assume that the process of removing the partition doesn't affect anything about the gases, their arrangement, their velocities, or anything like that. Okay, so these thought experiments are thought experiments. They're very powerful, and we can do that in a thought experiment. Okay, and so if it's not clear why I have to say that, think about it. Okay, it's because the instant you want to start the experiment, in our theoretical formulation is one gas on one side, the other gas on the other, okay? And requires some, you just have to think about how to do it. Anyway, all right, so you remove the partition, and at that instant, the experiment starts, and we know that you'll have irreversible mixing. The two gases, right, they're ideal, I remind you. They'll just mix, and at the equilibrium state, at the end of the process, both gases will be more or less equally dispersed throughout the container, okay, which is rigid. Okay, and the mechanical process by which that happens is diffusion. Okay, but now we sort of have this idea or intuition now that the driving force for this is going to be entropy. Okay, and so we want to see what value delta S takes for this process. So I think it's no secret that everyone would agree that this is an irreversible process. Okay, and so we have this mixing here, and so we want to look at this. And what is delta S for this mixing? Okay, so we know it's irreversible. Okay, so somehow we're going to figure out a way to do this reversibly. Okay, so we want delta S, right, mixing, and we know that that's going to be this 1 over T times dq reversible. Okay, and so our process is irreversible, right? And delta S, we know now, has to be computed by a reversible heat interaction. And so now we're going to have to construct a reversible process that allows us to get dq reversible to obtain dq reversible. And the great thing about S, which is a state function, is you can create the reverse process or something that is in the same direction. It doesn't matter. Okay, as long as you connect the two equilibrium states, you can either find a process that goes in the reverse way and then just flip the signs, or you could devise a process that goes in the forward direction and you don't have to worry about signs. Okay, so it doesn't really matter. That should not cause you any discomfort. And so in this case, we'll use a reverse process, just as we did with the Joule-free expansion. Okay, and here is the process that will connect the two equilibrium states. So the process then, which is reversible process connecting the two equilibrium states, is this. So we'll start with our mixed gases. Okay, so here we have Na plus Nb, they're all dispersed. So let's say this is A and this can be B, whatever. Okay, and they're ideal, so they don't see one another. Okay, and then in our initial state, so this is our final state, if you will, in the original experiment. So everything is mixed. But now in our reversible process that we're constructing, we're going to have these membranes. Okay, so we're going to have some sort of a membrane here that's attached to a piston. Okay. And on this side, we're going to have another membrane that's attached to a piston. And so what we can do with these pistons, these blue things, these lines coming out horizontally from both ends, is push them in. Okay, and so these membranes, so this membrane here, it's semi-permeable. They're both semi-permeable. This is only permeable, which means it only allows permeable only to A. Okay, and this guy is permeable, which means it only allows B to go through. So the piston on the left only allows gas A to go through it, gas B can't go through it. And the membrane, the semi-permeable membrane on the right only allows gas B to flow through it, and gas A can't go through it. So for instance, if you push the piston or the membrane on the left, which is permeable only to A, what's going to happen is as the membrane moves, all of the A particles are going to go through. They're not going to be affected. It's as though they don't see anything, but the B particles can't go through, and so the B particles are going to get pushed towards the right because they can't go through the membrane. It's like a wall. So for the B particles, that membrane is a wall, and so what that membrane is doing is pushing all the B particles towards the right. And likewise, the membrane on the right, since it's invisible to B particles, but the A particles can't go through, that piston, as you push it in, is going to move all the A particles to the left, okay? And the B particles are just going to not see it. So what happens then, right, as this piston moves, is that all the B particles will just stay where they are, and all the A particles will move towards the left. And you see what's going to happen here is that you're going to have separation. So at the end of the day, you'll have these two membranes that are permeable to either gas, okay? And what you'll have is, let's see, so the one on the left is permeable only to A, so you'll have Na left here, and this guy will have Nb. So you'll have only A on this side and B on this side. Okay, and again, the temperature is T. Okay, and this, of course, is going to be VA, and this will be VB, because we want to get back to our initial state. So does everyone understand that experiment? Is that everyone okay with that? All right, great. So let's move on. Let's analyze this process. And let me just say that delta S of the mixing is just going to equal, so this is demixing, if you want to call it that. Okay, because now, and of course, this is not going to happen spontaneously, and that's okay, because obviously we did work. There was some work done on the system to do this, so it's okay. We can do this, and this is how, you know, we separate things, and this is why things are so costly, right? If you make something as a chemist, you have to separate it from all the other things. That's demixing, right? And so that's why it's costly, because you have to do work. And so in this case, delta S mixing is just going to be minus delta S of demixing. Okay, that's fine because of state function nature of S. Okay, so let's analyze this thing. Okay, so we want delta S demixing, and I'm going to be excruciatingly, hopefully, looking at all the details here. So delta S demixing is equal to integral of 1 over T dq reversible, okay, which means then that we have to look at what is dq reversible. Okay, and for that, what we do is apply first law to get dq mixing, dq reversible. Okay. That's how we get our dq reversible. So let's apply the first law. So du is equal to dq reversible plus dw reversible. Okay. Now, since temperature is constant, right, so here temperature. So here we have N, which is equal to Na plus Nb, of course, and then V, which is equal to Va plus Vb, and of course here's T, and here we have T, so the temperature doesn't change. And we know that for ideal gases, U is only a function of temperature, so therefore du is equal to 0, which means delta U is equal to 0 because T is constant. These are ideal gases. So therefore, dq reversible is equal to minus dw reversible. And we know for an ideal gas what dw reversible is. And so this is just going to be P of T, V, and dV. Okay. and we don't have to worry about negative signs because dW is minus PdV. So minus times minus is positive. So dq reversible becomes P of TV. And that's the form that we have. Okay. Now, what we're going to do is that we have two components for work. Okay. There's going to be work that's associated with pushing all of the A particles to one side, and there's going to be work associated with pushing all of the B particles to one side. So there's two contributions to the work here, right? You can think of it this way, right? We could have, if we had started with the system on the left, our equilibrium state where everything is mixed, you could just move one of the pistons, let's say the left-hand piston, right? And you could just move it to the middle, okay? If you had just moved it to the middle, right, that would be one component of work, right? Or you could have started with the other way, and then you would have the other component of work. So there's two elements and two contributions to the work in this case. Is that clear? Okay. And so we're going to decompose the work then for the work done in moving A and the work done in moving B. So dq reversible, and now we can actually, let's see how we want to, so let's do this, 1 over T. dq reversible is going to be equal to 1 over T times PA. So we're going to have to look at PA, dV A plus 1 over T PB dV B. Okay, did everyone follow what I did here? So once I knew what dq reversible is from the application of the first law, okay, I could then proceed to getting this product 1 over T times dq reversible, because that's what I need as the integrand over here in this expression. Right, so that 1 over T times dq reversible, now I'm going to split up into two parts. One that's associated with the change in A, the volume of A, and then the change in the volume of B. Okay. And you see here that A and B change their volumes because here on the left-hand side, both gases have V as their volume. And on the right-hand side, gas A has volume VA and gas B has volume VB. Okay. Right. So we can now proceed. 1 over T dq reversible is equal to 1 over T. And now we just apply the ideal gas equation of state for P sub A, which is N sub A R, let's see, T, which is constant. And then we have a VA on the bottom, dVA. Okay, and then we have the same for the B particles, so which is NB RT VB times dVB. Okay, and very nicely, the T's cancel in both cases. So this T will cancel with that T. This T will cancel with that T. Okay. And so we're left with NAR, okay, 1 over VA dVA plus NB R 1 over VB dVB. And now it's really simple. We just do the integrations. Okay. So let me just rewrite this here. dq reversible. And so now delta S, and this is just, of course, ds for the demixing. Okay. And so delta S for the demixing is going to be the integral of 1 over T dq reversible. Okay. And that's just going to be NA and R are constant. So I'm just going to pull NA and R out, and I'll have an integral. So particle, so the volume of A goes from what? It goes initially from V, which was the sum of both volumes, to finally it's going to go to VA, right? And this is just going to be 1 over VA dVA. The same for NB, the integral. It's going to start at V total, and then it's going to go to VB. That was our initial state, 1 over VB dVB. Okay, and now we just do these integrals. That's pretty simple. Delta S D mixing is equal to NAR. This is just going to be a log of VA over V plus NBR natural log VB over V. So that's what we get for our delta S of mixing. Okay, so this is our intermediate result. Okay. Any questions so far? Those are, I think everyone probably has seen this in the reading, and these are very simple integrals now for everyone. And so since we're dealing with ideal gases, okay, we have these relationships, which I'm not going to prove. You've probably seen them already. And XB, these are mole fractions. Okay, so XA and XB are mole fractions. And I think everyone knows what mole fractions are. Just number of moles of any given species divided by the total number of moles. And remember, little n without a subscript is the total number of moles. Okay. And so for ideal gas, okay, because of the nature of ideal gases, XA can be written as V sub A over V, okay, where VA was that initial volume of A and the final volume if you're going in the reverse direction, and V is the total volume. And the mole fraction of B can be written as VB over V. And this is only because they're ideal gases. Okay, and that's something that you can prove to yourself. It's a very simple proof. So what we can do now is substitute in our VA over V and VB over V in these equation, in this equation, because it's an ideal gas, right? Because it's an ideal gas, we can write this. This does not hold generally, but because it's ideal, this holds. Our delta S for the demixing process is equal to NAR. VA over V is log XA, and plus NBR. VB over V is log XB. Okay. Any questions so far? And then finally, we know that NA is just XA times N from this expression. And NB is just N times XB from these guys. Okay, so this just becomes, NA is N times R times XA, natural log XA, plus on this side we have N times R XB times natural log XB, right? And all I did here was put an R between the N and the XA and the N and the XB. They're all multiplied, so it doesn't matter. And so we see here that we have an NR in both terms, so I can take that NR out. And then what I'm left with is XA natural log XA. If you want to put that there, we can. As long as you know what you're doing, you don't have to have them there. And this is going to be XB natural log XB. And that's the delta S of demixing. Okay. And then so for delta S mixing, we just have the negative of that. So it's minus NR XA natural log XA plus XB natural log XB. There you have it. So the entropy of mixing of ideal gases, so delta S for mixing of ideal gases, turns out to be this very simple expression, which has this prefactor that's related to the number of moles you have of the gases. And then it's all a matter of mole fractions that you have, okay? And we see here that since XA goes from 0 to 1, and likewise for XB, right? Natural log XA is going to be negative, and natural log XB is going to be negative. Therefore, that negative sign in front, when multiplied by the two negative signs that can come from each of these terms in the summation, is going to lead to a positive value, okay? Which actually makes sense then, because delta S mixing will become greater than 0. And this is exactly what we anticipated, because we know that that mixing process is irreversible. Once these things mix, you're not going to have them spontaneously and just, you know, instantaneously demix. You can wait forever and ever and ever and ever. You're not going to see that happen. Okay. So as we needed to have, that's what we get. Any questions, comments? So the entropy of the mixed state is higher than that of the demixed state. So let me just a couple of comments here. Okay. Let's take a look at this. This form for the entropy is kind of interesting, because if you think about mole fraction as a probability, right? Its mole fraction is sort of giving you this. It's another way of looking at probabilities, even concentration, right? Because concentrations are related to mole fractions in a way. They're a probability, because if you have, let's say, a system where you have mole fraction of 0.1, which means 10% of your system is a particular component, right? It's not too difficult to imagine it as a probability. So if you were to define some sort of volume in that system, it doesn't matter. It can be arbitrary. It can be arbitrary in size, okay, whatever size you want, some volume. And if you made many, many measurements that involve counting how many species you found in that volume element, okay, and you did this experiment many, 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 many times, what you would find is that 10% of the time you would find the species that had a mole fraction of 0.1. Right? And if you had another species that had a mole fraction of 0.8, 80% of the time you would find that species in that volume, regardless of what the volume is. So it becomes a probability. That mole fraction is a probability. And it's really cool that this XA log XA, which you can say is sort of like a PA log PA, and same for B, comes out to recapitulate this sort of expression that we found for the entropy, where we have the summation over states of PI log PI. It's kind of amazing that we see this symmetry in the macroscopic view, where we had no idea. We really didn't have to take into account all of these microstates. We just said, oh, well, delta S is equal to dq reversible, the integral of that, dq reversible over t. But we get this expression that is very highly linked to this probabilistic view of entropy, which turns out to be this constant times XA log XA. So this is just a sum then, right? Delta S, if you had many, many species in this ideal gas system, delta S mixing would just be minus NR, the sum over all species, right? So sum I is equal to 1 to the number of species you have, species of ideal gases. It would just be X sub I natural log X sub I. It's kind of amazing, right? It's the same form. Of course, in this case, there's a delta, but we see the same form of that thing. All right, that's very cool, very cool. The other point I want to make about this is that if we were to look at S, so I like this. This is cool. Okay, I like cool stuff like this. So this is cool. The other way is that if you want to look at S as KB log of W, right? This might be a little bit, I'm not going to spend too much time on it, but you can see here that if you have a demixed state, right? So let's say you, and we just take a look at these particles. So I'm just going to consider particle A, type A, okay? And it applies for B too. So initially A is in a lattice, right? And let's just say, for you can fill in whatever, right? There's going to be 10 to the 23rd. That's the order of magnitude we're looking at. Here, tic-tac-toe, look at that, right? So this is what you have for A, okay? And so the number of ways you can put the number of particles of A that you have in this lattice that's only half of the container is some number, right? So you can have WA initial, okay? But now, once you remove the partition and you allow A to move freely over more sites, right? So now you have WA final. And so let's say initially you have for A, and now I'm going to get all these, number of sites, what are we going to call it here? Sites initial. Initial. Factorial over some other factorials, okay? Finally, what we're going to have is sites final factorial over the same stuff, okay? And we see here that the sites that are available now to the same number of particles of A is going to increase, okay, in this case. And so the entropy contribution from allowing A to have many more arrangements, okay, is a positive contribution. And the same thing applies for B. And now, since they're ideal gases, A doesn't see B and B doesn't see A, okay, so we don't have to really worry about the two guys being at the same place. I mean, they're point particles. And so this is a nuance of the argument here. But since they don't see one another, they can actually be on top of one another. They can be on the same site because there's no interaction between them. This is screwy. I mean, this is, of course, this is not real, but it's okay. This allows us to see the conceptual underpinnings of how entropy plays into this process. And in fact, entropy increase. We have more arrangements now for A because we have a bigger lattice. So now we have many more different ways of putting all of the A particles that you started with on this bigger lattice. Same thing for B. And so from this point of view of what entropy is, and that is what it is, you see here that the entropy increases in this case. Okay. Any questions? So everything just becomes very consistent. All three pictures, this picture of entropy, it's not, they're all the same. This picture of entropy, the probabilistic, and the macro where we're looking at dq reversible over T, all converge to the same idea. Okay. And that's very cool. And that's very satisfying when that happens. It's very, very satisfying. It's a good feeling. Okay, so that's the entropy of mixing. Any questions on that? For ideal gases. And again, we have to qualify it as ideal gases. Okay, so at this point, what I'm going to do is sort of, I don't like to codify things, but let's just do that. Okay, so what it all boils down to let's do this. So for an isolated system, okay, if we have delta S greater than 0, okay, we have spontaneous process. Now I'm going to introduce some terms. This is called spontaneous process, irreversible. Okay. An isolated system. If delta S is equal to 0, this is reversible process. Okay. And delta S less than 0 is impossible. Will never happen for an isolated system. And we saw this earlier, but I'm just reiterating this thing. Okay. And so you see here for a reversible process, you can think of entropy now. Well, delta S is 0, but if you look at this from a microscopic point of view, what this means is that if you have two equilibrium states, equilibrium state 1 and equilibrium state 2, right? And there's some process, okay? Now what we're going to say is that it's reversible, right? So what we're going to do is put these double arrows. You've seen this in reversible chemical reactions, right? Well, now we'll just put this in terms of this abstract reversibility, right? What this means is that W1 and W2, what can we say about W1 and W2 now? Knowing what we know about entropy and reversible processes in an isolated system. Does anyone want to make a guess, or what's the relationship between W1 and W2? For a reversible process? Are they equal, greater than, less than?
Equal.
Yeah. Good. Right? They have to be equal, W1 and W2. And so for an isolated system, then the number of ways of realizing either of those equilibrium states is the same. And that's why delta S is 0. Okay. Any questions on that? All right. All right, I just want to do one other quick, let's see if I can do this quick, a couple of more quick examples. I'm going to move forward. Any questions, comments? Okay, so these next ones are pretty straightforward. Okay, so let's say we have heating or cooling at constant volume. V is constant, so dV is equal to 0. Okay. Well, to get delta S, that's just equal to the integral of 1 over T dq reversible. Okay. But we know that dq reversible at constant volume is just equal to Cv of T dt. Okay. So this becomes the integral 1 over T Cv of T dt from T1 to T2. And that's it. That's very simple at constant volume. Okay. So if Cv can be taken, if Cv can be approximated as constant over this temperature range that you're interested in, or perhaps the material has a more or less constant Cv, delta S is equal to the integral 1 over T, here's Cv dt from T1 to T2. The Cv is constant, so that comes out. So you have Cv integral from T1 to T2 of dt over T, but that's pretty simple. That's just T2 over T1. So what we get then at constant volume is delta S is equal to Cv natural log T2 over T1 at constant volume. Okay, any questions or comments? Okay, let's do one more. Another easy one. Okay. Here we're going to look at a reversible phase change. So here a substance is going to have a phase change. Either it's going to evaporate, it's going to melt, or sublime. Okay, so I think everyone knows what sublimation is, from the solid to the vapor. And it's a reversible phase change at constant pressure and temperature. Okay. And so an example of this would be H2O liquid, 100 Celsius, 1 bar. Okay. And this goes to, since it's reversible, you have H2O vapor. Let's see, I'll call it vapor at 100 Celsius and 1 bar. Right? So this is reversible. Everyone has been introduced to the idea of these phase changes as reversible. Okay. And so for this, we know since we have constant pressure, right? dQ reversible at constant pressure is just dH. Remember, that was our definition. At constant pressure, dQ reversible is dH. Okay. And so delta S for a process for this reversible change, in this case it's vaporization because we're going from liquid to gas, okay? Delta S is just the integral of 1 over T. And now 1 over T is going to be a constant because we know that this happens at constant temperature, right? Boiling, when you have boiling going on or vaporization going on, temperature doesn't change. Both the vapor and the liquid are at the same temperature. So we can call this T boiling, TB, okay, times dQ reversible. This is a reversible here. Okay. And that's going to equal 1 over T boiling times the integral of dQ reversible at constant pressure. Sorry, that's at constant pressure because this process is occurring at constant pressure. But we know that dQ reversible is equal to dH. And so delta S vaporization is equal to 1 over T boiling times the integral of dH for this process, right? And so so what this integral of dQ reversible means is that you just add up all of the dQs over the process, right, of boiling. So you start with 5 moles of liquid water, you let it all evaporate, and you see what dQ is for that process. Okay, that's what this integral of dQ represents for this process. But we know what that is. That's just the integral of dH. But the integral of dH over this process is just delta H of vaporization, right? Once this whole that integral is saying that take up all of these little bits of dQs as you're vaporizing everything from liquid to vapor, okay? So once that process, when you have no liquid left, that integral represents the net sum of all the Qs that were involved. And in this case, at constant pressure, each one of those little dQs is really just a dH. That's by definition, again, from the beginning of this course. And so we know that since H is a state function, the integral of D whatever, which is a state function, is just delta of that state function. And so delta S vaporization is just 1 over T boiling times delta H of vaporization. And you can have the same thing then for delta S of melting. That would just be 1 over T melting. It's probably not T melting, it's probably something else, times delta H of, I think it's fusion, that's what they call it, but we have the same thing when we're looking at melting, and you can have the same thing for delta sublimation, where you go from solid to vapor. Is just equal to 1 over the temperature where you have sublimation going on times delta H of sublimation. And there you have it. Those are very simple when you have these reversible phase changes. because in a reversible phase change, delta Q is, I misspoke. There is no delta Q. dq is just dH when you have these things at constant pressure. And so the expressions for entropy change are very simple. Okay. That's it for today. We'll do one rather, maybe somewhat semi-complicated problem next class for an irreversible process, and then we'll move on to some mathematical formalism that will allow me to show you why we can never get to 0 Kelvin, which is the thing I promised you a little while ago, to tie it back into the Carnot efficiency and everything about entropy. And then we'll move into thermochemistry. I hope to finish thermochemistry, and that will be something that we will have on our second midterm, which will be before Thanksgiving break. Okay, thank you all for your attention. I'm going to wish you all a great week. Sorry that it's well, if you're in Newark, it's gray and cold and wet, but I wish you all a great week, and I hope you're all safe and happy. And I will end the meeting there if there's no questions. Okay, great.
Thank you.
Take care, everyone. Thank you.